B2, and the fact that there are 2 lines here rather than 1, and the fact that we have this arrow here. Oh, sorry, that's B2. 3 lines here rather than 1 tells us something about the combinatorics of how the roots interact with each other. This one is B4. I hope I've got that right. C4, and so on. So irreducible here means that the diagram is all in one piece. It's connected. There are 4 infinite families of these things. The AN, and these correspond to SLN plus 1. The BNs, which correspond to odd special orthogonal groups. CNs, which correspond to symplectic groups. DNs correspond to even special orthogonal groups. So I talked about special orthogonal groups briefly before. Symplectic group. So what's a symplectic group? You take a non-degenerate antisymmetric bilinear form on k to the n. N has to be even for this to happen. And symplectic group is all of the invertible linear transformations of determinant 1 that preserve that form. So there are these 4 infinite families, and then there are 5 exceptional irreducible Lincoln diagrams. These guys here, G2, F4, E6, E7, and E8. And so bear in mind from what I was saying before that each of these Dinkin diagrams corresponds to a simple algebraic group. Actually, it corresponds to more than 1, because as well as SLN plus 1, we have the projective linear group PGL n plus 1. They have the same Dinkin diagram, but different fundamental group. So those of you who are familiar with the theory of Lie groups, you know that one of the invariants that you use in describing a Lie group is its fundamental group. And this thing here, if you make k into the complex numbers, then this is simply connected as a topological space, but the projective linear group PGL n plus 1 C is not. So there's a notion of good primes and bad primes. So the general philosophy here is that if your field has characteristic 0, then everything's much nicer. I mean, that's not to say that there aren't lots of interesting questions to explore for algebraic groups and characteristic 0, but the behavior is much nicer. The correspondence between the group and the Lie algebra is much nicer, for instance. And the general philosophy is that as long as the characteristic is large enough, then the algebraic group will behave in the same sort of way as it does in characteristic 0. But if the characteristic is small, then you can have strange things happening, like that example of the centre of the Lie algebra of SL2 that I was talking about yesterday. In characteristic 2, the centre of the Lie algebra of SL2 is actually one-dimensional rather than zero-dimensional, which is what the theory of Lie groups will lead us to expect. So there's a combinatorial definition of good primes and bad primes that I won't bother you with, but I can tell you what the good primes and the bad primes are. So 2 is bad for all of the simple groups except AN. 3 is bad for most of the others. Well, sorry, not most of the others, for all of the exceptional ones. And 5 is bad for E8. Okay, and nothing else is bad. So once your prime is greater than 5, it is good in this sense, and this means that your group tends to behave a lot better. For AN, which corresponds to SLN plus 1, we say that every prime is good. Nonetheless, as we saw in this example I was talking about a moment ago, SL2 is kind of strange in characteristic 2. So if P divides N, I think I meant P divides N plus 1 there. Yeah, I did. Yeah, so that's a typo there, sorry. And so if this extra condition is satisfied, then we say that the prime is very good. So a lot of the interesting questions and phenomena that come up in the subject happen when the prime is bad. So here's what I haven't talked about at all. So this is a huge chunk of the theory that I've completely left out. The while group, root systems, and root datum. So I think what I do in the exercises, and I hope to produce an exercise sheet later today that can be handed out and then you can have a look at before tomorrow, is I'll go through some of the stuff in the special case of SLN or GL, so you can see how it works there with things more concrete, and that will give you some kind of taster for what happens in the general case. So if you want to learn more about that, then these books here, Humphrey, Springer, Burrell, all called linear algebraic groups. You should read one or preferably all of those books. So for instance, the parabolic subgroups can be completely pinned down and described in terms of the root system. You can say exactly what they are. Okay, so the next topic, G complete reducibility, and finally here you see the definition. So from now on, G is going to be a connected reductive algebraic group. A lot of what I say makes sense for non-connected reductive groups, but everything's a little bit more complicated. For instance, you have to modify your notion of parabolic subgroup in the non-connected case, and this can be done, but just to keep things simple, I won't do it. So here's the definition. Take a subgroup of H of G. We say it's G completely reducible, or GCR for short, if whenever it's contained in a parabolic subgroup of G, it's contained in a Levy subgroup of that parabolic. Okay, so remember we have this notion of this special class of subgroups of G called the parabolic subgroups. Okay, a parabolic subgroup is a subgroup that contains a Burrell subgroup. A Burrell subgroup is a maximal connected solvable subgroup. A Levy subgroup of a parabolic subgroup is a maximal connected subgroup. Remember that. Got into that other black pen we had yesterday, so it's still kicking around somewhere. Oh. Here's the semi-direct product of any of its Levy subgroups and its unipotent radical. So remember, this is the maximal connected normal solvable unipotent subgroup. Okay, so this guy is uniquely determined. This L is not uniquely determined, but it's unique up to conjugacy. It's unique up to conjugacy. Okay, and then we say that H is G irreducible, or G for short, if H is not contained in any proper parabolic subgroup of G. And in the last sentence, it's immediate that A is G irreducible, then the H is, if H is G irreducible, then H is G completely reducible. Little exercise for you. Okay, you need to think for a moment to fill in the gap there. And the clue is to just remind yourself that H is a parabolic subgroup of itself, and then ask yourself, what do the Levy subgroups, the parabolic subgroup H, look like? Okay.
G is a parabolic subgroup itself.
Sorry, G is a parabolic subgroup of itself, yeah. G is a parabolic subgroup of itself. That's right. So another way of formulating this, so suppose H is contained in a parabolic subgroup P or G. We want to know whether H is contained in a Levy subgroup. So H is contained in a Levy subgroup so let's fix a particular Levy subgroup L of P. There are lots of them, as I said, but let's fix one. H is contained in some Levy subgroup of P, if and only if, well, the Levy subgroups, remember, are all conjugate. So if H is contained in a Levy subgroup, it must be contained in some conjugate of this one. So this will be the case if and only if H is contained in an RU P conjugate of L for some U in the unit nilpotent radical. But that's equivalent to saying that U inverse H U is contained in L for some nilpotent radical. Okay, so saying that H is contained in a Levy subgroup of P is equivalent to saying that some RUP conjugate of H is contained in this particular Levy subgroup that we chose. So that's a useful alternative characterization. We'll be using that a lot. So what about the special case GLNK or SLNK? So the whole point of this definition, as I said before, is that this should generalize what we mean by a completely reducible representation for GLN and SLN. So for GLN and SLN, this had better mean the same thing as completely reducible, and it does. So that's the statement here. H, if G is GLN or SLN, and H is a subgroup of G, then H is G completely reducible, if and only if the inclusion of H and G is a completely reducible representation. And the same thing goes, I didn't write it down, if you can replace G irreducible here and irreducible representation. We've kind of essentially we've proved this with a gap. I'll come back to that in a moment. So this first sentence here is what I just said before, that we want this to coincide with this new definition, to coincide with this usual concept for special linear and general linear groups. And so now this gives us a big source of examples. If we know a little bit of representation theory of algebraic groups, then this gives us a big source of examples of subgroups that are GCR and subgroups that are not GCR. We just have to find completely reducible representations and non-completely reducible representations of various H's, and this is going to give us lots of G completely reducible and non-G completely reducible subgroups. So let's take an example. Okay, the adjoint representation. L2K. Right, so remember any algebraic group acts on its Lie algebra. So SL2K acts on its own Lie algebra by the adjoint action. I don't remember whether I actually used this word yesterday, but this is the name for the way that the group acts on its Lie algebra. And so SL2K is an algebraic group of dimension 3. It's a variety, it's got a notion of dimension, it's a connected algebraic group of dimension 3. And so this is going to give us a three-dimensional representation. Okay. SL2K. That's on SL2K, the Lie algebra. And remember what this was. We could describe this as not all of the matrices in, not all of the 2 by 2 matrices, but the traceless ones. So I didn't use this notation yesterday. But this little bit of ad hoc notation, the traceless matrices. And it acts by conjugation. So as an exercise, I'm going to get you to write down this representation explicitly. Choose a basis for the Lie algebra, a basis for the traceless matrix, and write down this representation. And there's a sensible choice of basis to use, which I'll give you. And if you do this exercise, then what you'll find is that rho is irreducible. Characteristic is not 2. And there should be no surprise for those of you who know the theory of Lie algebras. If you have a simple Lie algebra, then its Lie algebra should be simple as a module. if you have a simple Lie group, then its Lie algebra should be simple as a module for the Lie group for the layer joint action. Okay, so this is no surprise. But in characteristic 2, something a bit strange happens. This not only is this representation not reducible, it's not even completely reducible. If the characteristic is 2. Oh, well, we've already seen this, or we've already seen part of this. Remember, I said that the Lie algebra of SL2 has a non-trivial center. Yeah. So this gives us a one-dimensional stable subspace. So this tells us that the representation is not completely reducible, is not irreducible. And to show it's not completely reducible, you just have to show that there's no stable complement. Any complement would have to be a stable two-dimensional subspace, and it's not hard to check that there aren't any. So this tells us that the image of rho for image is GL3K irreducible in the sense I've defined if the characteristic is not 2, and it's not even GL3K completely reducible if the characteristic is 2. So there's quite a nice example, I think, and it illustrates some of the problems that can come up in bad characteristic. Okay. Even talking about good and bad characteristic, we have to think a little bit about what that means. What we're really doing is we're thinking of SL2 in a more functorial sort of way. We think of SL2 as a functor. You give me a field, I give you the group SL2K. So what I'm doing is I'm thinking of fixing the type of the group SL2 and looking at what happens when I vary the field and what happens when I vary the characteristic of the field. So this is really what I mean when I'm talking about good primes and bad primes. And when I make statements like, as long as the prime is large, the characteristic of the field is large enough, then blah 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 blah. That's the kind of thing that I'm thinking of. So how do we prove this? So the argument that we went through yesterday with these block upper triangular and block diagonal matrices amounted to showing the following thing. So remember, I've referred to example 1.1, which is buried way back in the notes. So let me just remind you, in this particular case, we defined P to be the group of block upper triangular matrices. Is this pen getting a bit faded, is it? Okay, thank you. Okay, these ones are dead. I'll put them down here. These ones are not. This is a subgroup of GLNK, or SLNK, it doesn't really matter, the argument's the same. And this was an M by M block, and this was an N minus M by N minus M block. And if we had some subgroup H of GLN, then we showed that H stabilizes a subspace W of dimension m. If and only if H is conjugate to a subgroup of this group. And let me be very precise here, GLNK conjugate. When I just say conjugate, I mean conjugate in whatever the ambient group is here, but I have to be careful because in a moment I am going to care about which group it is that's doing the conjugate to a subgroup. P. H stabilizes a W as above and a complement to W. If and only if H is GLNK conjugate to a subgroup of this L that I talked about. And the L, so I'll write it over here, was the corresponding block diagonal group with the same block sizes. The same? Okay, so if H is going to be completely reducible, then it would better be the case that whenever H stabilizes a W, then it stabilizes a complement to the W. So therefore, it would better be the case that whenever H is conjugate to a subgroup of this, it should be conjugate to a subgroup of this. You have to be completely reducible in the sense of representation theory. But to be GLNK completely reducible, we actually need something stronger. By this alternative criterion that I've rubbed off now, we want it actually to be RUP conjugate. So we don't want H just to be GLNK conjugate to a subgroup of L. We want it to be RUP conjugate to a subgroup of L. So this is the subtlety, and so there is something that needs to be proved here. I'll come back later. And when I give talks about this stuff, when I talk about G complete reducibility, and I say, well, it's the same thing as complete reducibility for GLN or SLN, and I draw pictures like this, and then people in the audience sit there nodding their heads. At least that's generally what happens. But this subtlety here gets completely glossed over. So the nice thing about a course of lectures like this is that I have the chance to talk about some of these finer details. So I will return to this point later. Well, I think this will also be the subject of an exercise. I just have to make sure that I can do the exercise myself first. Okay, so we want some examples. We want some other examples. That's the first example, what happens for GLN and SLN, and that's satisfying. It coincides with this usual notion from representation theory. Here's the second example. There's a lot of stuff on this page here, but the upshot of this is that if you have a non-trivial unipotent subgroup, there's another typo, that should say of G. Maybe note these typos so I can correct them in the notes that get posted. So how do we see this? I wanted to spend a little bit of time going through this example because this foreshadows something that we're going to be talking about later. So there's this somewhat complicated looking construction here. The point of this is that suppose we have a non-trivial unipotent subgroup of G. So my claim is that this is not G completely reducible. Okay? So what do we have to do to establish this claim? We have to find a parabolic subgroup that contains U with the property that no Levy subgroup of this parabolic contains U. Right? That's what we need to do. And we call such a parabolic subgroup a witness to the fact that U is not G completely reducible. Right? Because this particular parabolic tells you, no, this subgroup is not G completely reducible. So we find a witness which I call curly P. So this is a parabolic subgroup. And what properties does this have? Well, of course, U should be contained in this parabolic subgroup, but actually we can say more. U is contained in the unipotent radical of this parabolic subgroup. Okay? And this immediately tells us that U cannot be contained in any Levy subgroup of this parabolic subgroup. Right? Because Levy subgroups have trivial intersection with the unipotent radical. Okay? So if L is a Levy subgroup of this P of U, then P of U is equal to the semi-direct product so in particular L has to have trivial intersection with the unipotent radical. Okay, this is true of any parabolic subgroup, not necessarily just this special one. Yeah. So if U is a non-trivial subgroup of the unipotent radical, it can't possibly be contained in L. So U is not contained in L. Therefore, U is not GCL. Okay. But what's really important about this guy is that it's canonical. Okay, it's somehow a best, or maybe I should be a little bit careful about using the word best, but it's canonical in the sense that if we have an automorphism of G that stabilizes U, it also stabilizes this parabolic subgroup. That's a very, very useful property to have. So perhaps I won't talk about the construction. The construction is written down there, and it's a little bit unsatisfying because there's all this structure theory of reductive algebraic groups that you need in order to prove some of the statements that are on the sheet there. And I can't do that because we haven't talked about the structure theory. This is all explained in this is his book. Yeah. So don't worry too much about the structure. There will be one question about these U's in the exercises, which should be fairly straightforward. So this thing is canonical. So if phi is in order G, I didn't actually define order G, but you can probably guess what it means, what the notion of an automorphism of an algebraic group is, and order G is the group of these under composition. So if phi stabilizes U, set-wise, not necessarily point-wise, but set-wise, then phi stabilizes P of U. And that comes from the construction. I say here it's obvious from the construction. If you look at the construction, basically you have a completely deterministic algorithm for getting this P of U from U by taking normalizers of things and unipotent radicals of things. And all of those constructions are well behaved undertaking automorphisms. Okay. Well, what kind of automorphisms does an algebraic group have? Any group has inner automorphisms, right? It acts on itself by conjugation. So the normalizer of U, any element of the normalizer of U, is an automorphism of G that stabilizes U, by definition of normalizer. So this normalizes P of U. But parabolics in a connected reductive group are self-normalizing. So if this thing normalizes this parabolic, it has to be contained in this parabolic. Okay. And now we see a nice consequence of this. If H is not reductive, something HG, then H is not GCR. I've written something slightly more general on the sheet here. I've said, oh, actually that's on the next page. I've said that if your subgroup H has a non-trivial normal unipotent subgroup, then it's not G completely reducible. So this is a special case because if H is not reductive, then it has a non-trivial normal unipotent subgroup, namely its unipotent radical. So proof. H normalizes its own unipotent radical, which is non-trivial if H is non-reductive. Okay. Therefore, by what I've written up here, so H is contained in the normalizer of the unipotent radical. Therefore, it's contained in this canonical parabolic. Okay. And now I claim that H is not contained in any Levy subgroup of that parabolic, but that's easy because we've just seen that this unipotent group is not contained in any Levy subgroup of the parabolic. So this larger group H can't be contained in any Levy subgroup of the parabolic either. U of H is not contained in any Levy subgroup. I'll just be lazy and write Levy of P of U of H. So H isn't either. Okay. So we have proved that G completely reducible subgroups of G have to be reductive. Okay. So let's pursue this line of thought a little bit further. Down the bottom here we have a definition. A linearly reductive group H. What does that mean? That means that every rational representation of H is completely reducible. This question actually came up yesterday. Someone asked me when we were talking about representations, do I mean representation or rational representation? If H is an algebraic group, then by a rational representation of H, we mean a representation that is a homomorphism of abstract groups from H to GL in K. And the word rational here means that this representation should actually be a homomorphism of algebraic groups. So not just a homomorphism of abstract groups, but a homomorphism of algebraic groups. And remember that means that it should be a morphism of varieties. Okay? Where does the word rational come from? It's because you think of the functions associated with a variety. You think of the coordinate ring, elements of the coordinate ring you think of being as being polynomials in some sense, or more generally one can consider rational functions, ratios of polynomials. So take a linearly reductive group. What can we say about that? Well, first of all, a linearly reductive group is reductive. That's a little exercise on the sheet. That follows from stuff that's on the previous page. Okay, so I'll leave that as an exercise. But in fact, we can say more. If H is a linearly reductive subgroup of G, then H has to be GCR. Okay. Now, if you take a reductive group H and a connected reductive group G, and you put H inside G in various ways, then sometimes the image will be G completely reducible, and sometimes it won't be G completely reducible. That depends on the embedding. Yeah. So being a G completely reducible subgroup depends not just on the structure of the subgroup H, but on the way in which it is embedded in G. Okay, that's important to remember. Here we're saying that if the group is linearly reductive, then it doesn't matter how you put it inside G. It always has to be G completely reducible. Okay. So maybe I should write down an example of what I just said. It's not in the notes. So let's take SL2 and characteristic 2, and let's think about putting SL2K inside GL3K. Now SL2K is not linearly reductive. We've already seen that because I said that we have a non-completely reducible representation, namely the adjoint representation. So the adjoint representation and this is not completely reducible. Or maybe I should start using the language I've developed. So what I mean here is that the image is not completely reducible. Okay, this is a GL3 completely reducible. This is a property of images. But here's another way to put SL2K inside GL3K. You just send a matrix A and SL2 to do the stupid thing. You just send it to the block diagonal matrix, which has A in the top left-hand corner and a 1 in the bottom right-hand corner. And this is completely reducible. The image is GL3. So this shows that we can put the same group inside the same H inside the same G in two different ways. In one way the image is completely reducible, the other way it isn't completely reducible. Okay? I'm cheating here slightly because the image of these representations is not the same. The image of this is SL2, this is a faithful representation, but the image of this is quite subtle. You look at this and you say, well, SL2K, the adjoint action of SL2K on its Lie algebra is faithful. What's the kernel of the adjoint action? It's the center. And SL2K doesn't have any center. The group SL2K doesn't have any center because plus or minus the identity matrix are the same. So this is a monomorphism of abstract groups, but it is not a monomorphism of algebraic groups. This is a subtlety here which I hope to return to in one of the exercises. So this is worth remembering. An isomorphism, if you have two algebraic groups that are isomorphic as abstract groups, they need not be isomorphic as algebraic groups. And this is yet another instance of the bad things that can happen in small characteristic. So what do linearly reductive groups look like? The second sentence on here. I know I said this already. Any linearly reductive subgroup of G is GCR, and one can prove this using ideas from cohomology, which I'll be talking about a little bit later. So what do linearly reductive groups look like? Well, in positive characteristic, there aren't very many. Basically, the only linearly reductive groups are extensions of the torus by a finite group of order co-prime to the characteristic. Okay, so H0, the identity component, is a normal subgroup. I didn't say that before. Nonetheless, it's true. And the quotient is finite because H modulo H0 you can think of as being the set of connected components of the variety H, and a variety has only finitely many connected components. That's why this quotient is finite. But in characteristic 0, any reductive group is linearly reductive. So that says in characteristic 0, if you have a subgroup H of G, it will be GCR, H will be GCR, if and only if H is reductive. So that's not so interesting. That means that you don't get these subtleties that you can put the same group inside the same G in two different ways and have a G completely reducible one way and not G completely reducible the other way. Okay? And because we're only interested in exciting stuff, we'll assume from now on that the characteristic is possible. Just because most of what I'm going to say from now on, I think pretty much everything I'm going to say makes sense in characteristic 0, but mostly is rather trivial. And it will just simplify some of the statements if I don't have to keep saying if the characteristic is 0, then this happens, if the characteristic is positive, then this happens. Okay, this is probably a good place to stop for our 5-minute break. There's L, yeah. Sorry, that should say N here. Good, thank you. Very useful to have alert people in the audience. Thank you. Yeah, this was this result of CR, that if you have a subgroup of a Levy L, then it's LCR, if and only if it's GCR. But in general, the answer is no. And there are some easy and obvious counterexamples. Since the question's about to disappear, maybe I should write it up on the board where we can see it. So M and G are connected, reductive. And then the question is it true that HM completely reducible is equivalent to HG completely reducible? So there's our question. Oops. So one problem that comes up, I wanted to mention this because this is related to some ideas that Alan talked about, kind of fusion problems. So we have a subgroup H of M, we want to know whether it's MCR, we put it inside a parabolic subgroup of M, and then we want to know, is it conjugate to a subgroup, sorry, we put it, is it conjugate to a Levy subgroup of that parabolic? Perhaps I should write this down so I don't get too confused. So this is a parabolic M. Okay, I have to be a bit careful here because I have two groups lying around in which I might want to talk about parabolic subgroups. So I want to know, so I pick a Levy subgroup P, and then I want to know my razor is. P conjugate to a subgroup of L. Okay, so remember this P is living inside M. So is H even M conjugate to a subgroup of L? Okay, so certainly the answer to this question will be no if the answer to this question is no. Because this group is living inside this group. And the kind of fusion phenomena that you can have, I use the word fusion problems there, but perhaps Alan would take offence at that term, because this fusion is the kind of thing that this is her bread and butter. Where these are opportunities rather than problems, right? H might be G conjugate to a subgroup of L, but not M conjugate to a subgroup of L, because these subgroups might fuse inside the larger group. So that's a problem. That's a problem you can have. Another problem is that H might be contained inside a Levy subgroup of a parabolic subgroup of G, but not contained in any parabolic subgroup of M. It's another problem that we might have. Anyway, here's an obvious counterexample. You just take H equal to M, sitting inside G, where M is not GCR. Then H is MCR, because any group is completely reducible in itself. Right? In fact, M is M irreducible. Right? Remember, that means not contained in any proper parabolic subgroup. Obviously, the whole group can't be contained in any proper subgroup of itself, right? So M is trivially M irreducible, therefore it's M completely reducible, but M equals H. So H is M completely reducible, but it's not H. It's not G completely reducible. Okay, so that's a very obvious and easy example. What about examples in the other direction? Can you have a subgroup that's completely reducible in the big group, but not completely reducible in the small group? That's harder, and the answer, generally speaking, is no if the characteristic is large enough. I think we will be coming back to this point later on. So here's an example. I'm not really able to explain the details because they involve calculations in the group G2, involving the roots of G2, which I haven't talked about. So you take G, a simple group of type G2 and characteristic 2, you look at the short root subgroup. So this is a connected semi-simple subgroup. What does this notation mean? Remember, I said that the semi-simple group is essentially a product of simple groups. Okay? So this means that this group is essentially a product of two simple factors, each of type A1. Type A1 means SL2. Okay? So you take what's essentially an SL2 cross SL2 subgroup inside this group G2, and then you can put a copy of S3 in there in such a way that it's GCR in the bigger group, G, but not MCR in the smaller group, M. And my PhD student, Tomohiro Uchiyama, found related examples for groups of type E6, E7, and E8. Now, E8 is a massive group, and it's hard to do any kind of meaningful calculation in E8, so I'm quite impressed that he was able to say something about E8. But once he'd figured out what was going on in this example, he was able to find some other examples. Here's another example involving symplectic groups. I waved my hands around a bit before and told you what a symplectic group is. So here we have, I've souped up this construction somehow. We have a connected reductive M inside a connected reductive G. So what's G? G is SL2M. M is a symplectic group SP2M. Okay, so remember I told you that a symplectic group is a subgroup of some special linear group that preserves some form. Yeah. So symplectic group is automatically sitting inside a special linear group. It's natural representation. It's called. It turns out that you can put SPM cross SPM inside SP2M, kind of block diagonally if you write things down in the appropriate way. And then you can embed SPM diagonally inside this product of two copies of SPM. Okay, so this gives us an H, SPM inside a K, which is SPM cross SPM, inside an M, which is SP2M, inside a G, which is SL2M. Now H is K completely reducible, and that actually follow. You can see that quite easily from the result I wrote down before about products. So that one's easy to see. It's G completely reducible. That's also not so hard to see if you think of what's happening in terms of these blocks that I was talking about before. But H is not M completely reducible. And in order to see that, you have to know something about what parabolic subgroups of symplectic groups look like. And we have time to talk about. So this actually gives a counterexample to both directions of the question. And this example was due to Martin Liebeck. Very kindly let us put it in our paper. So now, gosh, I'm a bit ahead of myself. So an application to finite subgroups. Okay. So I think probably most of you know that if you have a finite group F and look at ordinary representations, so representations into GL and C or some other field of characteristic 0, a finite group has only finitely many isomorphism classes of n-dimensional representations, right? And the ordinary representation theory of finite groups is all about finding out what these representations are via character theory and then saying stuff about their pattern. But these representations are completely reducible. This means that their images are GLNC completely reducible. Yeah? What happens well, there are two questions here. First, what happens when you replace GLNC with an arbitrary connected reductive G? And the second question is, what happens if you go in positive characteristic? Okay, so let's look at the second question first. Well, I guess this is looking at both of them together. In positive characteristic, if your characteristic P, so P from now on was always the characteristic, it's positive at some prime. If that doesn't divide the order of your group, then there are only finitely many conjugacy classes of subgroups that are G that are isomorphic to F. So this is, so maybe there is something I can write down here. There's this confusion that comes up a lot between looking at subgroups and looking at representations. So Mashka's theorem is about representations from this finite group F into GLN, so GLNC. Although exactly the same works for any algebraically closed field characteristic 0. Yep, and it says there are only finitely many isomorphism classes. Isomorphism classes correspond to conjugacy classes in the appropriate sense. Really, I'm more interested in images or representations because I'm interested in subgroups. But because these are finite groups, if I take a particular image, there can only be finitely many possible representations that give me that image, right? Because this is a finite group, so there are only finitely many ways to embed it inside another finite group. So saying that there are only finitely many conjugacy classes of representations tells me that there are only finitely many conjugacy classes of copies of F inside GLNC. If I'm talking about faithful representations, if I'm talking about arbitrary representations, then it's saying there are only finitely many conjugacy classes of groups isomorphic to quotients of F. But again, because F is finite, there are only finitely many possible quotients of F. So really what Maschke's theorem tells me is that GLNC has only finitely many conjugacy classes subgroups isomorphic to F, and each such subgroup is GLNC completely reducible. Maybe I should put some quantifiers in here. This is saying for every finite group F and for every N, GLNC has only finitely many conjugacy classes that are isomorphic to F, and moreover they're all GLN completely reducible. And exactly the same things are true if in positive characteristic, the characteristic does not divide the order of the group. Still true if the characteristic is positive, and still true if we replace GLN with an arbitrary reductive G. Maschke's theorem proper is about GLNC. If you want to get the same result for arbitrary connected reductive groups G, then you have to do a little bit more work. There's a paper of Slotterby, which talks about this, although it doesn't actually give a proof, but a full proof, but it sketches some of the ideas around the proof. But what if P divides the order of the group? Then things become very different. Even just SL2K as infinitely many conjugacy classes of subgroups isomorphic to CP cross CP. This is the product of two cycle groups. That's an exercise. And I didn't write this down, but also the subgroups are not not SL2K completely reducible. Or at least most of them are not. And there's a reason for that, which is the theorem down the bottom here. Take a finite group and any connected reductive G in any characteristic at all, then there are only finitely many conjugacy classes of G completely reducible subgroups. Okay, so if you just concentrate on G completely reducible subgroups, then you recover the same nice finiteness result from Maschke's theorem. So this is of interest if you want to study finite subgroups of connected reductive algebraic groups. The proof of this involves quite a lot of work. So this is the paper of mine from now on. So I just had a question about how you prove this statement here. I can't remember off the top of my head. Here's another characterization of linearly reductive groups in positive characteristic. group is linearly reductive if and only if every element is semi-simple. And I can give a reference to a paper in which this is proved. But I have to admit, I've never actually read the paper, so I don't know really how the paper goes. Okay, a little bit of history. So G-complete reducibility was introduced by Serre, like so much else. And one of his main interests was in the theory of spherical buildings. So I'll go through this quite fast, I think, because it's a bit incidental to the rest of what we've been saying. It's interesting. So if you have a reductive algebraic group, then you can make a spherical building, associated spherical building. So what's a spherical building? It's a very special kind of complex. Okay. What does this simplicial complex look like? The simplices are the parabolic subgroups of G ordered by reverse inclusion. Okay. And we can think of this as an abstract simplicial complex, or we can think of it more concretely as a topological space. So simplices are generalized triangles, if you like. Whether a lecturer has ever been killed by a falling whiteboard. Okay, so here's a three-dimensional simplex, a tetrahedron, and whenever you see one of these kind of abstractly inside your simplicial complex, you can think of it as a little topological space, and you form the simplicial complex by gluing these guys together. Now remember I said yesterday that the conjugate of a parabolic subgroup is a parabolic subgroup. So the group G acts on the building by conjugation, because conjugation by G moves the simplices around. So take a subgroup H of G, then you can look at the fixed point set. So this will be some subset of the building. It will be a subcomplex, in fact. It will be the set of all parabolic subgroups of G that are fixed by H under conjugation. Okay, so that's all of the parabolic subgroups that are normalized by H, but remember that parabolic subgroups are self-normalizing, so that's saying all the parabolic subgroups that contain H. And Serre showed that H is G completely reducible if and only if this subset of this topological space, this building, is not contractible, where contractible is the usual topological meaning. So that's quite a striking result. And using building theoretic ideas, although there are other proofs, Serre proved that if L is a Levy subgroup of G, by which, remember, I mean a Levy subgroup of some parabolic subgroup, and you have a subgroup of this Levy, L, then H is GCR if and only if it's LCR. This is a very useful result.
Excuse me, is it called spherical building because of some geometric realization? And could you please give an example?
Not so easy.
No is the short answer to the second part of the question. This is some kind of huge. Why is it called a spherical building? That's because as part of the definition of a building, it's a simplicial complex that comes with a notion of special subcomplexes called apartments. You can think of the building as being made up of these apartments. And although the building is kind of big and infinite dimensional, the apartments are not. They're finite dimensional. And the name spherical and spherical building comes because the apartments are Euclidean spheres, divided up into, chopped up into simplices. So I have a nice picture of this somewhere on my computer. I'll try to draw this. So for A3, so for SL4, the apartments will be two spheres chopped up into triangles. So maybe that gives you some hint of what's going on. And the building is the union of kind of infinitely many of these. And the language of the algebraic groups, the apartment, an apartment is the set of all parabolics that contain a fixed maximal torus. Okay? But there are lots and lots of different maximal tori. They're all conjugate, remember, but there are lots and lots and lots of them. The field is infinite, so this gives you lots and lots and lots of apartments. Okay? There are this G-complete reducibility theory that I'm talking about has quite close relationships with some stuff to do with spherical buildings, but I don't have time to talk about that, unfortunately. I'm happy to talk about that.
Well, maybe it's a good idea in this audience to recall what contractible means.
Contractible means that you can continuously deform the space to a point. Okay? So the two-sphere, you can't continuously deform to a point. That's not so obvious, but if you kind of think about what you would have to do, then you can't. However, if you punch a hole in it, if you punch a hole at the South Pole, then you can contract everything continuously up to the North Pole. Just slide every point around the Great Circle to get up to the North Pole. And this fails if you don't take the South Pole out, because then you don't know which way the South Pole should go, and you kind of have a discontinuity at the South Pole, because these 2 points here, very close to the South Pole, are being pulled in opposite directions. Yeah, thanks. Good suggestion. Okay, Liebeck and Seitz, I mentioned this before, they did a lot of work on the subgroup structure of simple groups of exceptional type. They wanted to know in particular what the connected reductive subgroups of such groups would look like. And they proved that under mild restrictions on the characteristic, with p greater than 7 is enough, every connected reductive subgroup of G is G completely reducible. So the same thing that happened, remember, in characteristic 0, any reductive subgroup is completely reducible. So the same thing happens as long as the characteristic is large enough. And their main idea was the use of non-abelian cohomology. So what's this about? Take a proper parabolic subgroup of G, called the uniponent radical V, just to disable some writing, and take a Levy subgroup. Maybe I should write some stuff on the board here. So, in particular, I should remind you that this notation pi L that appears up here, this is this canonical projection from a parabolic subgroup down to a Levy subgroup. Remember that P is L semi-direct product V, where V is the uniponent radical. Yeah? So you get this for any choice of levy. You fix a choice of levy, you have this projection. Pi sub L. If you choose a different levy, you get a different projection. Yep. And then, so if you have H contained in P, then H acts on V by conjugation. Pi L H V pi L H. Okay. So this gives an action of H on V. So it's an action in the sense of action of the group on the set. It's also an action in the sense of geometric invariant theory, which I'm going to be talking about next time. But more. So remember, whenever you have a group acting on a set, then each element of the group gives you some bijection of the set. In this case, these bijections are actually group automorphisms of this group. Yeah? Because conjugation by something is going to give you a group automorphism. And whenever you have a group acting on another group by automorphisms, you can talk about the one cohomology. I'm not going to give you the definition of the one cohomology now, but I will give it to you in the exercises. And as an exercise, I will get you to work out some of the details of what's going on here. That's It's not a difficult exercise, it just involves a little bit of calculation. One cohomology, H1 of H with coefficients in D. So some of you, I'm sure, will have met the idea of group cohomology when you have a group acting linearly on a vector space. And you can talk about the cohomology of the group with coefficients in that vector space, or coefficients in a module, or something. This is a non-abelian generalization of this, because the group V, the unipotent radical, need not be abelian. Okay. So remember, even for G, SL3, okay, and let's just take the standard for L of upper triangular matrices. The unipotent radical of that is the upper unitriangular matrices, and it's very easy to see that this is not abelian. So unipotent radicals are usually not abelian, but parabolics are hardly ever abelian. So we talk about non-abelian one cohomology. And then the point of this is that if the one cohomology vanishes, then H is going to be V conjugate, or RUP conjugate to a subgroup of L. And this is precisely what you want when you're trying to prove that H is G completely reducible. You want to prove that if you can put it in a parabolic, then some P, then some RUP conjugate of it is contained in a Levy subgroup. So one approach to this is to prove the vanishing of the appropriate one cohomology. So these non-abelian one cohomologies are difficult beasts. Richardson proved that if H is linearly reductive, this is the last sentence here, then the one cohomology is trivial. So that's one way of proving that a linearly reductive subgroup is always GCR, using this argument here. You put your H inside a parabolic, the one cohomology vanishes, therefore H has to be inside the Levy. So how do you actually do that calculation? The non-abelian one cohomology is very difficult to deal with. In the world of abelian cohomology, you have nice short exact sequences and long exact sequences, and you have all this machinery that you can use. So what do you do here? Although V is not abelian, it's at least nilpotent. So unipotent groups are nilpotent. Perhaps I should have said that before. And what this means is that you can slice V up into layers, each of which is abelian. You can take a filtration. In fact, not only is each layer abelian, that's these quotients here, it's actually a vector space, and H acts on it linearly. Okay? And so you can get at the one cohomology of V by looking at the one cohomology of each of these pieces, and here you have a group acting linearly on a vector space. So you have all this extra machinery from the world of abelian cohomology that you can use. And Liebeck and Seitz showed that if H is connected and reductive, and the characteristic is large enough, then these guys here just tend to vanish, okay, for reasons to do with representation theory of algebraic groups. And then they deduced that this thing vanishes, and that let them show that these subgroups H have to be GCR. So this work is being continued by David Stewart, who has looked at the same kind of problems, but without the characteristic assumption on P. And so therefore, in that case, not surprisingly, the one cohomology doesn't always vanish, and you can have subgroups that are not G completely reducible. Okay, there should be no surprise. We know that there are G's with non-completely reducible subgroups, and then that connected reductive subgroups. This adjoint representation of SL2K that I was talking about before is an example. And so whenever you're in that situation, that's telling you that some of these one cohomologies at least have to be non-trivial. Okay, some more results. Take a product of connected reductive groups and take a subgroup of the product, then that subgroup is completely reducible of the product, if and only if its projection on each of the factors is completely reducible. Okay? And the reason for this is simply that parabolic subgroups of a product are products of parabolic subgroups of the factors. And similarly for Levy subgroups. So once you have that fact, this is quite easy to prove. So I'm not going to go into the details. You can check this for yourselves. Similarly, if you have an isogeny of connected reductive groups, you get the analogous property. If you have a subgroup H of the group upstairs, G1, it will be G1CR if and only if its image is G2CR. And again, the proof is you look at the relationship between parabolics upstairs and downstairs and Levy subgroups upstairs and downstairs. And this is buried in Humphreys or Burrell or something somewhere. That tells you that the image of a parabolic upstairs is a parabolic downstairs and vice versa. So again, not hard to prove. So here's an interesting question, I think. You have a connected reductive group sitting inside another connected reductive group. So you have a connected reductive group M sitting inside another connected reductive group G. And then you have a subgroup H of M. So H is sitting inside M. You can ask, is HM completely reducible? H is also sitting inside G, so you can ask, is HG completely reducible? And then the question is, what is the relationship between the answer to those two questions? Is it always the case that H is M completely reducible if and only if H is G completely reducible? Well, not surprisingly, when you ask a very general question like that, the answer is no. But a lot of the work that my collaborators and I have done is centered around answering this question in various special cases. If you put hypotheses on M and G, what can you say? So one example, if L is a Levy subgroup of G, then the answer is yes. This
You
was
mean
this.
M is L.
M, yeah, Bacon Riller, and this is an earlier paper of mine. But the original ideas came from work of Winberg. So maybe because we have just a few minutes left, I will just sketch one or two of the ideas there because they feed into the stuff about G-complete reducibility that we're going to be talking about later. Okay. Take some positive integer capital N. Look at the Cartesian product of capital N copies of G. G acts on this by simultaneous conjugation. So what do I mean by that? Take an n tuple of elements from here. Take some element from the group capital G. How does this act? You just conjugate each of these entries by this fixed little g. Okay, so this is an action. So for me, actions are always left actions, by the way, for the same reason that I always write my functions on the left, because it's the correct thing to do. So we are now in the setting of geometric invariant theory. G is an affine variety. The Cartesian product of varieties is a variety. We have a reductive algebraic group acting on a variety. Geometric invariant theory says, and I'm going to be talking about this later, it says we can form a quotient variety. Quotient variety in the sense of geometric invariant theory. So often people write this quotient with two slashes to indicate that it's a quotient in the sense of geometric invariant theory. There's there's a reason for that, which maybe I'll talk about briefly next time. That's because this is not quite a set theoretic quotient. Okay, when you form some quotient space, you want the points in the quotient space to be the orbits of the group action in this case. It turns out that in order to make a variety, you have to throw some of the orbits away. Okay? In this particular case, you end up keeping most of the orbits. Now, n connected reductive substance. G. We can play exactly the same trick for M. M is contained in G, and therefore the product of n copies of M is contained in the product of n copies of G. Okay? And now what we get induced by this inclusion is a map of quotient varieties. Okay, this we have a well-defined map, and you can kind of see that you get a well-defined map on the level of set theoretic quotients, because if two tuples from here are M conjugate, then they're certainly G conjugate as well, because M is a subgroup of G. So you get a well-defined map from here to here. Certainly at the level of set theoretic quotients, and for the geometric and variant theory quotients, you can make this up. So let's call this. I really should have a capital N in there somewhere to label the dependence on N, but I'm going to leave that out. Theorem. So this is Winberg in characteristic 0. And itself in characteristic P. Says that this map is a finite morphism of varieties. I don't expect you to know what that means, because most of you don't have so much background in algebraic geometry, but one of the properties of a finite morphism of varieties is that its fibers are finite. Okay? Now, if you think about what that would be saying, for a set theoretic map here, that would be saying something like that if you have a bunch of tuples over here that are all G conjugate to each other, then they fall into only finitely many M conjugacy classes. Okay, that's kind of what this is saying. This is unfortunately not exactly what this is saying due to subtleties in the construction of the quotient. That's the way to think about it for the purposes of this talk. So this means that you can translate finiteness statements about conjugacy classes of things over here to finiteness statements about conjugacy classes of things over here. And so in particular, if you have some G that you're interested in, you can put it inside GLNK. So you think of this as being your M, and this guy here as being your G. Okay? So finiteness statements that you make in GLN, which tend to be easy to prove because you have all of this extra machinery, you have stuff about representations and characters and all this extra stuff, you can then translate into finiteness statements over here. So that's one way in which you can get at this extension of Nash's theorem, and that's how you prove this result that I wrote up before this theorem down here. Okay, I think this is a good place to stop.
This is all